One of today's most prominent and advanced physicists, Michio Kaku, has recently shared his opinion on a revolutionary discovery that could redefine our understanding of the universe. Recognized globally for his outstanding contributions to both classical physics and quantum mechanics, Kaku has confirmed that the James Webb Space Telescope, JWST, has detected 6 massive galaxies that, according to current scientific models, should not exist. These findings have the potential to unlock entirely new dimensions in our comprehension of cosmic evolution. As such, this development is both exciting and significant, deserving close attention. Michio Kaku, a distinguished American physicist of Japanese heritage, is widely regarded as an expert in experimental physics and quantum theory. Unlike many conservative or skeptical scientists, Kaku remains open to revolutionary data, including the astonishing results from the JWST mission. The fact that such a respected figure in science has chosen to speak out highlights the importance of this discovery. His enthusiasm and amazement are evident in his comments, describing these newly identified galaxies as among the most intriguing astronomical observations to date. Throughout his career, Michio Kaku has demonstrated a willingness to entertain new theories. He has long acknowledged that Einstein's equations of relativity and Newton's laws, while foundational, are insufficient for fully describing the complex workings of the universe. The discoveries from the JWST may offer an opportunity to expand upon existing scientific frameworks, but many in the scientific community are still hesitant to revise established cosmological theories, particularly those supporting the Big Bang. Kaku is not among them. He even finds humor in the sleepless anxiety some scientists experience when confronted with data that challenge their long-standing views. The James Webb Space Telescope discovered 6 enormous galaxies that date back to the earliest epochs of the universe, just 200 to 700 million years after the Big Bang. Surprisingly, each of these galaxies contains more stars than the Milky Way, despite their incredibly young cosmic age. The team responsible for the discovery has dubbed these galaxies universe breakers, because, if confirmed, they would force a complete rethinking of cosmology. This contradicts the prevailing theory that, after the Big Bang, the universe remained chaotic and formless for hundreds of millions of years before stars and galaxies began to emerge in a meaningful way. Some of the galaxies detected by the JWST are even larger than the Milky Way and display intense luminosity, suggesting that yearly hundreds of new stars are formed, whereas our galaxy only forms stars sporadically. It remains unclear exactly when the first galaxies formed, but existing models posit that the process began with individual stars or small star groups, which gradually merged to form dwarf galaxies and, over time, larger structures. However, these massive and organized galaxies from the early universe seem to defy that timeline, increasing the likelihood that either the universe is much older than we thought, or that galactic evolution occurred far earlier and more rapidly than believed. This revelation is difficult for conservative science to accept. Some physicists strongly resist these implications, suggesting potential measurement errors in calculating the galaxy's ages. Michio Kaku addresses this skepticism by noting that many outdated theories have persisted solely because of the prestige of their proponents. In science, especially in physics, it is the responsibility of experimentalists to keep theorists honest. Without reliable experiments, theoretical physics lacks grounding, highlighting the fact that we still know very little about the universe. The true origins of the cosmos, the Big Bang theory, established on the basis of observations in 1927 of the universe's expanding size, suggests that the cosmos originated from a singularity and has been expanding ever since. At that time, it was difficult for people to accept that the universe had a beginning, let alone an end. The prevailing idea was that the universe was eternal and infinite. Even today, many scientists struggle with the idea that there is a limit beginning to all existence. Yet the importance of entertaining alternative possibilities cannot be overstated. especially when empirical data no longer aligns with traditional models. New JWST observations seem incompatible with what researchers have assumed for decades about the Big Bang theory. However, science thrives on reevaluation and openness to new concepts and theories, continually tested and revised based on new evidence. When Einstein was a child, people believed that stars and planets were fixed in the sky. We now know that everything in the cosmos is in motion. Planets orbit stars, stars move through galaxies, and galaxies themselves travel vast distances through space. Much of this was inconceivable in earlier times. Today, scientists must similarly adapt, understanding that theories are provisional, not absolute, until validated through careful observation. The concept of the Big Bang gained momentum from Hubble's discovery that galaxies are moving away from one another with their velocity proportional to their distance from Earth, a connection known as Hubble's law. Supporting evidence, such as the cosmic microwave background radiation and the redshift of light from distant galaxies, bolstered this model. Still, it's vital to remember that in the past, people had seemingly solid evidence that the Earth was flat or that the Sun orbited us, until better technology revealed otherwise. Now, with the advent of the JWST, we are facing a similar inflection point in our understanding. Scientists expected the James Webb Space Telescope to verify the Big Bang model, but instead, it uncovered 6 massive and seemingly impossible galaxies. This unexpected result underscores how science is constantly evolving. Researchers must remain open to reevaluating theories in light of new discoveries and evidence. One essential tool used in this cosmic research is redshift, or the Doppler effect, which describes how the wavelength of light changes based on the motion of its source relative to the observer. For instance, when a star or galaxy moves away from us, the light shifts toward redder wavelengths. If it moves closer, the light shifts to bluer tones. Physicists use redshift values to calculate velocities and distances in the universe. But even small measurement errors could significantly affect their conclusions. As a result, scientists are now revisiting previous measurement techniques to determine whether the JWST's findings are due to redshift miscalculations or represent genuine anomalies. It's essential to conduct a thorough examination and peer review of the data and methods used in this research.